In this lecture, we will do something fun. We will learn how to compute the statistics of data streams and use the statistics in order to do motion detection in video. So let us get started. Suppose you have a sequence of numbers like this sequence S. You can compute the average and the standard deviation simply by saying np.average of S or np.std of S. Okay, so we can print them out, and this works well enough. So imagine that instead of having a single data point, you have a stream of data points. Maybe you are reading the temperature of something at regular intervals. And assuming we want to know the average reading and the standard deviation of the reading, we can write code as the following. We can define a function read stream that returns a random number. I mean, this should return a sense of reading, but to experiment a bit, we just will use a random number. And assume that we also have a method use that takes a number as parameter, that is, the use of the number. And so we can write this code, loop forever. We read a value, we append it to our sequence of values, we print out the average, and then we use the value. Okay? And then we stop after 10 because we don't want to keep forever doing that. Okay, so this is a sequence of averages that we print out. Now, I want to do something better, because the problem of this code is that it mixes reading of the stream and using it with computing some statistics. And what I want to do is essentially encapsulate the computation of statistics in its own class. I do this because we want to play around in this class with how to compute statistics in different ways. And so I don't want to have to modify the code in the middle of somewhere else. I want the statistics computation to be its own class so that I can have various versions of it, try one and then try the other and improve it without touching the rest of the code. So let us build a class for computing stream statistics. The class is given below, and I call it full averagerator because it computes the statistics of the full sequence it has seen. So it has an initialization method that does nothing, that takes no parameters and just sets to empty the sequence the object remembers. Okay, and it has an add method by which you pass it one more sample, and then it has an average property by which you can read the average, and an std property by which you can read the standard deviation of the sequence. So the implementation is as follows. Internally, I store the sequence of values. When you give me one more value, I append it to the sequence. And when I want the average or the standard deviation, I simply compute the average and standard deviation of the sequence of the values I have. Okay? So there are two steps in designing this class. The first one is figuring out which methods you need. In this case, we want to be able to add a sample and then read the statistical properties. The other step is to figure out the implementation, and in this case we went for the simplest possible implementation. We store the sequence of values as it is, and then we can compute the average and standard deviation on demand. So let me run this cell so we can use it. I can build an averagerator, an object of the class, and then I can use it in the above loop. So I can write it as follows. I read from the stream, I add it to the reading from the averagerator, and then we print out the average, and then we use it. Okay, so this should work. It works. And you may complain it's not very much different, okay? But the real advantage is that if I now change the implementation of full averagerator, or if I have many other types of averagerator, this code will not change, okay? The only thing that will change is the kind of averagerator object that we pass to it. So we'll be able to experiment and improve on the full averagerator without having to modify how we use it. This is one of the important ideas in computer science. You try to encapsulate functionality in such a way that when you wanna improve on a piece of the design, you don't have to modify the other pieces of the design, right? You want to build a bit of independence between the pieces of the same software system. Let us illustrate with a picture how this works. So here I introduce some plotting code from a matplotlib. And so let's look at the picture first, okay? Here I show you the axes, as I call them, so the raw data, and the smoothed axis, that is the running average, right? So the code looks like this. I loop 200 times, I read from the stream, these are just random numbers between 0 and 1. And I remember what I read because I want to be able to plot it. Then I add the reading to the averagerator, and I add to this smooth axis the average, so that then I can plot the axis and the average of the axis, okay? And it produces a plot below. We see that the axes are all over the place. They're just random numbers between 0 and 1. And the averages instead, tend to 0.5 actually as time goes on. So that's a nice picture, and we'll be producing more of these in the future. Now let's go back a second to our averagerator class. The question is it well done? Well, sort of. It's a very simple implementation. But the problem is it's not incredibly efficient because we have to store the entire sequence here, right? So if you want to do the average of a million readings, you will have to store a million element list. And the fact is that it's not really actually needed. We can do a little bit better than this. And it will be useful for the future also to do better as a stepping stone to more sophisticated implementations. So think at it a moment. Do we really need to keep all the data? And the answer is no. Because to compute the average of n numbers, you can do as follows. You can compute their sum, and then you can divide the sum by the number of numbers you have. So if you remember at each time the sum of the numbers and how many numbers you have, when you get one more piece of data, what do? You increment the sum. You compute the new sum including the new piece of data, and you compute n plus 1, which is the new number of data, and then for the average you do the ratio between the sum, the new sum, and the new number, okay? So we can do the following. Instead of keeping the whole list, we just keep the sum of the samples and the number of samples. When you get one more sample, what you do is this. You increment the sum to include the new sample, as we did here, right? And you increment the number of samples. And then when you ask for the average, what you do is that you return the sum of the samples divided by the number of samples. So this gives you the average in a much more efficient way, because you don't have to store the entire list. This works for the average, but what to do about the standard deviation? We can think at it as follows. So the standard deviation S is the square root of the variance V. And the variance V for a sequence of numbers x1, x2 to xn is given by the expectation, think at E like average, the expectation of x minus E of x, the whole thing squared. That is, it's the expectation of the square of the difference between the value and the average. So you can see that the variance essentially captures how much the sequence varies around the average, right? Because the distance between a data value and the average will be 0 if all the data are equal to the average, and otherwise if the data deviates from the average, this difference will be larger. If you square it, you end up with a positive value. And so the expectation of these is a good measure for how variable your sequence is, okay? Now, this is the definition of variance, but the problem is that this formula is not suitable for us to compute variance in an efficient way. The problem is the following. Imagine you are giving your sequence x1, x2, x3 up to xn, one data point at a time. It is easy to compute the average without having to remember the whole sequence. That's what we did above, right? So mu we can compute easily. The problem is, can we also compute the variance easily using the above formula? The answer is no, unfortunately, because when we are at the end of it, computing mu is easy, but to compute the expectation of x minus mu square, we need to do the average of x1 minus mu square, x2 minus mu square, x3 minus mu square, and so on. And this we cannot do without remembering the x1, x2, x3, and so on and so forth individually. So, yes, this is a beautiful formula. We know how to compute mu based on the sum of the values and the number of values, but we don't know how to compute this formula without actually remembering all the values. What we need to do is that we need to work a little bit on this formula here and put it into an equivalent form which is more amenable to computation. So we can do it as follows. Here I simply copy the definition. You always start like this in math, right? When you don't know what to do, you copy the definition and you try to work your way forward. So the variance is equal to the average of x minus mu square. Now, let us develop this square, okay? So I can write the average of, and in the brackets I can put x square minus 2 mu x plus mu square. Now, expectation is linear, so the average of a sum is equal to the sum of the averages. Okay, so I can break out these three pieces by wrapping them individually into the expectation operator. So I can say that this is equal to the expectation of x square minus 2 mu the expectation of x plus mu square. Okay, because the expectation of mu square is equal to mu square, because mu is a constant at that point. You know, the only random variable here is x. Once I break it out in this form, I have a little bit of luck, because there is a simplification we can do. What is e of x? E of x is mu. And so this is just 2 minus 2 mu square. That simplifies with the plus mu square to give just minus mu square. Okay, so the passage from here to here is simply algebraic. You know, the only thing that I use is linearity of expectations in order to break up the single expectation in the sum of the three expectations. Okay, but we are here, and so I can write that we have that the variance essentially is equal to this thing here. Now, these we can compute on the fly. In this case, we are lucky, because mu we can compute on the fly, right? I told you before how mu is simply the sum of the values divided by the number of the values. And to compute the average of the x squares, this is just the average of the x squares, yes, but just an average. So we know how to compute averages on the fly, right? We just keep the sum of x1 square plus x2 square, etc., and we divide the sum of the squares by their number. That's what the average of the squares is. So to be more precise, I can compute the sum of the squares. So I have Qn, you know, Sn was the sum of the numbers, Qn is the number of sum of the squares, and then E of x squared is simply equal to Qn divided by n. And so our variance will simply be given by Qn divided by n minus mu square. This we can implement. And so the implementation is as follows. I give you a class that is called efficient full averagerator. And so it keeps the sum of the x's, what I called S. I can add it here if you will. Okay, this was big S. And the sum of the x squares, which is what I called Q. And also the number of samples. When I get one more sample, what I do is quite simple. I increment the sum of the x's, and I increment the sum of the x squares. The latter, you know, I add x squared to it. And also, you know, I incremented the total number of samples. The average is as before, you know, it's the total of the samples divided by their number. And for the variance, I directly use the formula above. So I say that, it's a standard deviation. So I computed the square root of the sum of the squares, that is Q, divided by the number of samples minus mu square. And then I take the square root of it. Okay? So this enables me to compute both standard deviation and average without having to remember the whole sequence of values. This is essentially a gift from the god of mathematics. it's not clear at all, actually, that it should be so simple to compute statistics of a stream of data without remembering all the data samples, okay? If we were to try these for percentiles or for medians, you would have to go through much more complicated algorithms to try to approach the problem. It's really a sort of gift from mathematics that averages and standard deviations can be so easily computed of a streaming data without having to actually remember all the pieces of the stream. It's a fantastic gift, because if the stream of data becomes large, as we will see in the future, or in the future of this class, really, you would have to use a lot of storage for just for computing the statistics. So let us give it a try. And here I can use the efficient full averagerator and produce a plot. Okay, and we are plotting like before, the axis, the smoothed axis, which is the average, and also the standard deviation. And the standard deviation, I do a little bit of computation below. You can check it to see that it should converge to the value of 1 over square root of 12. And if you can follow the math below and convince yourself that that is the value that it should have as limit. Now, this is very good, but let's try to play with it a little bit more. So here I have a simulation of a noisy temperature. Temperature varies during the day and night. So here I model it as simply as a sinusoid plus some random amount of noise. You can read the code if you like, but what I want to do is simply show you the graph. You see there is a sinusoidal basic variation on which there is overlapped a little bit of noise. In reality, temperatures don't quite have such a simple cycle. They decrease typically a little bit faster in the evening to how they increase during the day, but at any rate, this is good enough to play with. Now, imagine that our thermometer is a bit noisy, and every now and then it takes a faulty reading. I don't know, it could be that somebody opens a window and there is a cold draft, or somebody puts a hot pan close to the sensor, but every now and then there is a disturbance, okay? So here I model the disturbance by simply adding every now and then a larger random value. So let me do it for you. Let me just show you the result. Actually, you can read the code if you like. So you see, these are the noisy readings, and every now and then there is a big spike. So can we use our averagerator to actually remove the spikes? So the idea is the following, right? The standard deviation gives us a measure of how far the typical data is from the average. So if we know the average and the standard deviation, and we see a point that is really a lot further from the average than the standard deviation, maybe we can assume that it's a spike and remove it. Okay, so this is the idea, but does it actually work? Let's give it a try. So let's compute the average and standard deviation of these noisy temperatures readings with spike noise as well. And if we do this, we see the following. So the blue line as before are the noisy readings with random noise. Every time I run the cell, I get a little bit of a different random noise and spikes. So let me show you, right? And the orange line is the average, and the green line is the average plus the standard deviation. And the problem is this, that the average and standard deviation applied to a signal such as the temperature don't really measure the noise, right? Because the noise is a short-term noise. They essentially are much more affected by the diurnal cycle of the temperature. And so look at this spike here, this one here. This spike actually has the effect of taking the temperature and make it more close to the average. Just because it's increasing, a nighttime reading essentially. So you see, we cannot simply remove the pieces of the temperature that are too far from the average, because we would be essentially removing the daily maxima and minima. We need something different. This signal has a daily component, and we need a sort of average and standard deviation that are not computed on the entire signal. They are computed on like a portion of its recent history. So that, if we have a reading every minute, we are just computing the average and standard deviation over, say, the last half hour. we can maybe still detect an outlier, but we are not influenced in our estimation of the properties of the signal by its long-term behavior. We want to focus on the short-term behavior to remove these spikes. So how can we do this? And there are various approaches to doing this. One approach is to implement a sliding window averagerator. If you think at it, the original averagerator computed this final average by going from 0 to that point, right? So it uses the whole history. A sliding window averagerator has a fixed size of history that it remembers. For example, if the window size is 100, when it computes the average at 400, it would include only the data between 300 and 400. So if you computed, for example, the statistics with a sliding window size of only 20, you would have a much smaller range of the signal and perhaps remove some of the daily variation out of it. Okay, so the sliding window averagerator simply computes the same average and standard deviation computations, but just on a fixed size of the most recent data. I ask you to implement these, so I don't give you the solution. I ask you to actually implement them. Let me give you a little bit of a suggestion on how you to go about implementing a sliding window averagerator. Imagine that you're receiving data. This is one data point, another data point, another data point, another data point, another data point. Imagine your window size is 4. So when you have received this data, you have to compute your sliding average according to these 4 pieces of data. Okay? Then you get one more piece of data and you need to compute the next sliding average, which will be computed according to these data. Okay? So the problem is the following, that to compute the new average, you have to get the new data in and you have to kick the old data out of the average. And so there is really no very good way of kicking the old data out without actually remembering the old data. That is the problem. So there is no elegant way to compute sliding window averages that does not involve remembering all the data that are in the sliding window. So when you try to do your implementation, remember that there is nothing better to do than for you to remember all the pieces of data that actually go into the sliding window. So it may seem strange to you because sliding averagerators sound simpler, right? Because they are based on less data. But actually, it's more efficient to implement a full averagerator like the original one we had, in which you start always from the beginning, than a sliding one in which you just look at a fixed number of the most recent data. Strange but true. This actually is a big problem. Nobody likes to remember so much data. You know, if your window size is 100 or 200, you would need to remember 100 or 200 data points, and it's an unpleasant idea. So there is a much more pleasant solution that is really quite beautiful, and I want to talk about it, which is called, or I call it at least, a discounted averagerator. It has the following idea. So if this is a sequence of data points, okay, the last point will be worth 1. The one before the last will be worth alpha, where alpha is a discount coefficient smaller than 1. It's called discount coefficient. Okay? So the one 2 steps in the past is only worth alpha square, alpha cube, alpha to the 4th, and so on and so forth. Okay? So these coefficients are the weights of the data. And I can do a weighted average rather than a normal average. So essentially I give much more importance to the most recent samples than to the ones that are far away in the past. This is an idea that is really taken a little bit from economics. In economics, $1 today is worth $1. $1 tomorrow is worth only alpha. Why? Because you would rather have the money now than tomorrow, because if you have it now, you can use it in the time between now and tomorrow. If you only have it tomorrow, you only have it tomorrow, right? So it's better to have money now than in 1 year. That's why, when you ask for a loan, what are you really saying? You're saying that you want money now and you will repay it later. And to do that, you have to actually pay more and interest over your loan for the privilege of having money sooner, right? So this discount factor, the fact that things are worth more today than they will be in the future, if they are given to us, is a fundamental idea in economics. And here we are actually using sort of the reverse to it applied to the past to compute our averages, right? What's happening today, we remember it more strongly that what happened yesterday that has faded by a factor of alpha, the day before yesterday that faded by alpha square, and so on and so forth. Now, you may think, okay, but this seems even crazier than window averages. And I tell you, no, this is not crazier. It's actually not crazier. Because remember that to compute averages, I had this trick. I could keep S, which is the sum of the numbers, is equal to 1 to n of xi, and I can compute q, which is the sum from I is equal to 1 of n of xi square, and then I can say the average is equal to s over n, and the variance is equal to q divided by n, which is the average of the x square minus mu square, right? These were the formulas we derived. Now, if I do it for a discounted sequence instead, how does this work? Well, we never computed S and Q in this way. We simply say S is equal to S plus xn, now when we get a new value. In fact, S plus x, let me just give you the update. And we say Q is equal to Q plus x square. That's what we did in practice. Okay, and also n is equal to n plus 1. So these three fundamentally were the updates to compute the statistics for a sequence. If we go to discounted sequences, the idea is as follows. We can just replace these three equations, okay? We can say that S is equal to alpha S plus X, because the previous sum has been shifted behind by 1 day, and so it's worth only alpha less than what is going on today, which is X. And so by the same token, Q is equal to alpha Q plus x square. Okay, we also discount by alpha the history of the sum of the x squares. And for n, we say n is equal to alpha n plus 1. And if we do these substitutions, then we can simply use these same formulas. Incredible but true. So these formulas are true always, provided we compute these numbers in a different way. So this is for discounted and this is for all time. Okay? So let's put this idea in practice into code. So this is a code for the discounted averagator. It takes as initializer a value of alpha, of course, which we store. And then, just as before, well, instead of calling it n, I call it w because I call it weight. But this is what n was before. So I set the weight to 0, I set to 0 the sum of the x's and the sum of the x squares also. And you see that the updates are very similar to before, except that I discount by a factor of alpha what is in the past. So when I compute the new weight, it's equal to the old weight times alpha plus 1. Before I had, n, self n is equal to self n plus 1. Now I discount the old value. The same I do for the sum of the x's, and the same I do for the sums of the x squares. So this is the difference in how I do the update. And actually the formula for computing averages and standard deviations is exactly as before. There is no change. So with these, let's play around a little bit, and I want to show you what happens visually. Okay, so this is our data. I added a bit more noise than before just to illustrate better what's going on. And if I compute now average and standard deviation with alpha is equal to 0.9 and plot the results, I would get something like this out. Okay, so the blue data is the raw data and is a bit noisy. The discounted average cleans it up, essentially, right? Because it removes these short-term variations. Here we also have an incredibly interesting effect. Not only does the discounted average removes the noise, but it also introduces a small delay. You see, the original sinusoid had a maximum around here, and the smoothed one a bit later. And here the minimum of the raw data here, and the smoothed one is there. It makes sense that we're introducing a delay because when we do a discounted average, the discounted average will contain the most recent data, but also some of the older one. And so the discounted average always trails a little bit behind the raw data. But the fact that you cannot clean up a signal without introducing some delay is actually a fundamental fact of mathematics and also of the physical world in the end. Cleaning up the signal essentially means determining its basic frequency, right? So the basic frequency would be determining the basic sinusoid behind it, cleaning up the noise. And the delay represents essentially your uncertainty about the position. And it's a sort of fundamental fact that you cannot know of a signal both its frequency, that is its underlying sinusoidal nature, and its position. Let me make, in fact, a small excerpt from this. In physics, when you have a particle that moves, what the particle really is in quantum dynamics is a trainlet of waves. So it's something like this. Okay? So the wave train is where the particle is, and the momentum of the particle, the product of mass times speed, right, is tied essentially to the wavelength. Okay, the higher the momentum, the shorter the wavelength. And the position is the position of the train of waves. And you have a fundamental result that really derives from the theory of Fourier transforms that says that you cannot at the same time measure the wavelength and the position. Okay? Because to measure the wavelength, you have to consider an interval that is big enough for you to have information about the wavelength. And if you do that, then you don't know about where the particle is in the wavelength, right? So you can either know very well what the wavelength is or where the position is, but you cannot know them at the same time. This is essentially Heisenberg's uncertainty principle. And it turns out that what we are doing when we compute averages is an operation that is very closely related to Fourier transforms. Actually, it's related to the Laplace transforms that you use and the Z transforms that you use to study digital signal processing. Digital because we don't have continuous time, we have discrete time, but it's very much the same kind of soup, so to say, mathematically speaking. And so we cannot at the same time recover the underlying sinusoidal signal without introducing a delay. It's essentially Heisenberg's principle related to data smoothing, if you so will. Okay? To see the phenomenon of the delay even clearer, we can just plot, remove the noise and do a plot, in which case we would have like this result. The blue line is the original one, and the orange one is the one in which we have used the averagerator and plotted the average. We can use these to do outlier detection. So let's return to our noisy sensor. Now that we know how to compute an average only of the most recent data, we can actually use this short-term average and short-term standard deviation to try to remove outliers from a signal. So let us try it. I show to you visually what happens. So the blue is the raw signal, the orange is the average, and the green is the average plus and minus 2 standard deviations. 2 standard deviation plus gives you the interval around the average where roughly 95% of the data is. Okay, so we can say essentially that things that are outside of 2 standard deviations from the average may be fake signals. Okay, this doesn't remove all spikes, but you see that the big spikes are the one that essentially punch through the green line, and the green line increases a bit as a consequence. So whenever the blue line punches through the green line, those are big enough outliers that would be detected by the 2 standard deviation criterion. Okay, you could use a 3 standard deviation criterion, a 4 standard deviation criterion, that's up to you. But if we use a 2-1, that's what happens. We can run it again. In this case, we remove most outliers, but that's not always the case, right? Well, here we were lucky again, I guess. Here as well. And let me run it a few more times. For example, you see this outlier is not removed. And you have a few that are not removed by the 2 standard deviation criterion. So you could do these to reconstruct a smoother version of the signal. Basically, whenever the raw signal is further from the average than 2 standard deviations, you could throw away the data point, which you consider to be faulty, and you can replace it with the average. And we could be doing this, but actually I will ask you to do it. I will ask you to implement this clean data class that essentially does what I told you. It computes these discounted averages and discounted statistics, and when it finds data points that are too far from the average, throws them out and replaces them with the average. So I have already implemented the data cleaner class. Let me show you how it works. So the blue one is a noisy signal, the orange one is a clean signal. You see the orange and the blue overlap, except when the blue one has a big spike, the orange one instead uses the average. Okay? So here there are some tests for your code. And now if you look at these, an alternative idea would be the following. Look at the standard deviation. Whenever there is an outlier, the standard deviation increases by a lot. Of course, right? Because the standard deviation measures how noisy the data is, and the outlier is actually fed into the average rate or as part of the data itself. And so this seems to be wasteful, and you may think, wouldn't it be better when I detect an outlier to actually not feed it inside the data but keep it out? You know, in this way I would have a tighter standard deviation, and I would be able to detect outliers even better. Because you see, after an outlier, there is big space for another dirty data. In this case, you know, everything went fine, but if you had the 2 outliers in a row, or maybe a few in a row, you could risk that the later outliers are missed because the standard deviation has become too permissive, essentially. So let me run it a couple of times and see whether we can see the phenomenon. Yeah, you see, here there are 2 outliers, they increase the standard deviation, and when there is this other outlier here, well, it's considered to be good enough, simply because, you know, now the outliers increase the standard deviation quite a bit, and we are very permissive. So can we write a better solution of the data cleaner class in which we avoid feeding outliers to the statistics? Well, let's give it a try. So the try is actually here, and if you do that, you see that it absolutely fails. Because the point is that at some point, when the first thing will go wrong, you will start to believe that your real data is an outlier, and you will start throwing it out. And then you will become fixated on the fact that you are right, and everything you are getting is wrong, and you will be completely stubborn and not change your mind. It's incredibly difficult to build, and in fact I don't know how to do it, frankly, how to build a class that is able to throw away outliers and yet not consider them into the statistics. Maybe machine learning can do that, but certainly not the simple approaches we are using to compute running averages that we have now. Okay, if you don't fit data in the statistics, you run the risk of not only throwing away the outliers, which is what you want, but also disregarding a changed reality that you should be listening to. Imagine that your temperature sensor is maybe always in the cellar where the temperatures are very constant, and you become convinced via data analysis, a variation of over 1 degree is suspicious. And then you take it out and you put it into your attic, and the swings of temperature go crazy between day and night. You cannot simply reject all the new data because it doesn't fit your prior mental model. You need to be able to always accept the new data and reset the statistics around it. And so that's why the previous approach, even though it sometimes fails for individual data, is much more robust.